Hello everyone, it's A-Level, final exam time on Friday for Unit 4. The WJEC, in their infinite wisdom, have only taken parts of some of the units out. Now, vast parts, most of those units, but it is worthwhile recapping some of it. Most of this stuff you would have seen before, we have done before, or you've encountered it at GCSE or AS, but there are some important changes and some past paper questions that we need to look at before you go into your proper revision this week. That's what this video is for. Watch it, try the past paper questions, make sure you can answer them because it is most likely the content in this presentation will appear in your exam. So let's start here. And I know you're saying this, I know you're thinking, you what, mate? Because some of your teachers, I'm sure, will have taught you that some of the sections are completely missing. And in actual fact, that is what most of us have been doing, because so much of the content that they've said is going to be in there is huge. Those big chunks of topics that we've covered in Unit 4. However, they haven't removed any complete units. They've only removed parts of units. So we're going to be going through all the parts that should still be in there. Some of these are a little bit weird, so you have been warned. Okay, so Unit 1, Hardware and Communication. These are the parts that we need to go through. Architecture, and that is the structure mainly of the CPU, but also of the entire unit of the system. Identify, describe the main components of a contemporary computer architecture. They're using the word contemporary very loosely there. Describe and explain the limiting factors to parallelization in a parallel process. Okay, we'll talk about that. And then calculate the runtime of a given result. This is learning a small formula. It's easier than you think, but it does need to be included. Here is a diagram that represents the architecture of a CPU. These symbols are important and you may need to be able to reproduce them, but as far as I can tell, they don't actually mean anything in the real world. The upside down trousers represents the ALU, the arithmetic logic unit, the bit that does the actual mathematics and the logic. We have a control unit, which is responsible for maintaining control of the system and basically generating the clock cycle. So that's responsible for the speed at which the instructions are processed. And then we've got our registers. Registers are our fastest, smallest pieces of storage in the system. All instructions need to be in the register for them to be processed. But let's have a little look at the registers that we need to know about, because it's not just that. We need to know about a few important ones. The PC, or the program counter, is the register that holds the next instruction number that we're moving to. That's quite important. Then we've got our accumulator, which stores the result of any arithmetic or logic command or any loading or any input. The CIR, the current instruction register, stores a copy of the current instruction in case we need to work on it later. The MDR, the memory data register, stores a copy of the current piece of data that we're working on. And the memory address register stores, you guessed it, a copy of the address that we are currently working on. So please keep in mind, everything is stuff that we're currently working on except the PC, which points to where we're going next. Those registers form part of the architecture of our CPU, and the information is sent around via buses. These are essentially very, very fine cables or traces on our silicon, which allow the information to flow in and out of the CPU and between the components. The control bus carries the control signals, so essentially next, 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 next. Overclocking, by the way, is just increasing the speed of those control signals, which generates more heat and takes more electricity. Our data bus shockingly carries the data, and the address bus, I know you're going to be surprised at this, carries address data. A CPU has registers, as we've just said, which are really fast, small bits of memory, but it can't hold an entire program. The cache memory on a CPU stores a copy of the most commonly used instructions. So if the CPU wants to go and get the next set of instructions, it can, and hopefully they should already be in the cache. If that's the case, they will load really, really fast. If they don't, it's called a cache miss. The CPU on the left has a bigger cache than the CPU on the right, so we'll probably have cache misses less often and therefore run a little bit quicker. A core is the processing part of the CPU. Basically, in a very simplistic way, you can think of what a core is, where the processor is able to do one thing at a time. So a single core processor can only do one thing at a time. On the right, we've got a quad-core processor that can do 4 things at a time. An 8-core processor can do 8 things at a time. A 16-core processor can do 16 things at a time. So what we do is we break the job down into 4 parts, and we process it all at the same time and put the answers back together to get our finished version. There is, of course, a problem with that. Not all jobs are parallelizable. We can't break down everything into its constituent parts and get a result back. And that's particularly important if my next instruction is based on the result of my previous one. But things that are parallelizable and highly parallelizable are things like graphics. Anything multimedia can be parallelized really well, but some instructions are single core only. AMDAHL'S law is a way of calculating the time it takes to process data on a multi-core machine. So you need to remember this equation, So Tn, or the time it's going to take us on n cores, is equal to the time it takes on 1 core, and that could be in hours, in minutes, whatever, multiplied by the fraction of the algorithm that's sequential, they'll probably give you this as a decimal, plus 1 over the number of cores multiplied by 1 minus the fraction that is sequential. So essentially, we are trying to multiply the time taken by how much the algorithm is sequential and a fraction of it that's not. Let's give you an example. In this case, I'm going to say T1 is 6 hours. There are 12 cores, and 0.8, i.e. 80% is sequential. That means that most of the process needs to go one after the other. That turns into this, which once you work it all out and do all the maths, you end up with this calculation, which gives you 4.8996 hours, which is the processing time it would take with 80% of it being sequential and 12 cores, which makes about some sort of sense. And therefore, you should be able to work out that very, very quickly. Do practice it, do go and learn that formula, because if they ask you to do it, you will have to apply AMDAHL'S law very, very quickly. The CPU is then connected to memory. Primary memory is our RAM. That is volatile though, so and it's not massively big, but basically everything that is active on your computer should be stored in RAM at the moment. Our secondary storage, or our hard drive or our SSD, is significantly slower than the RAM, but can store everything in a mode that it will be saved when the power goes off. Our cache then sits between the primary storage and the CPU, and there are usually multiple levels of cache, with the biggest level of cache being at the outside and the smallest level being on the inside, so that more instructions are stored further away from the computer, and it decreases as it gets, more instructions are stored closer to the CPU, but as we get closer to the CPU, the cache size becomes less and less and less. We also have our inputs and output devices, which can send interrupts into the hardware. Now, that diagram makes some sort of sense, but let me show you the diagram that WJEC wants you to use. It's this. They're very fussy as well about the direction of the arrows. You've got your CPU, which is exactly as we've got there, your input and your output device, and your memory. The only real difference is the arrows. So if you look, we've got a line going from input device to output device into the control unit with no arrows on. That's the control bus. That's the control signal. That's the bit that's going next. Then our registers have a back and forth with memory, and also an ability to push information straight to memory that goes through the data bus, which is also connected to the input devices and the output devices. Types of memory, the main reason we have so many is that the closer we get to the registers, the faster the memory is. However, it's also very expensive, so it's smaller in capacity and much more volatile. In other words, the power goes off, we lose the data. On the other side of the spectrum, far away on the opposite side with the hard drive or the SSD, it's much, much slower in terms of speed, but the capacity is going to be significantly higher. It's also going to be non-volatile, which means that when the power goes off, that data will still be saved. Let's look at a past paper question then. 3A, draw a diagram to identify the hardware and communication elements of a von Neumann computer system and how they're connected. Well, it is just that diagram we drew, or we looked at just now, but let's see where the marks come from. 1 is for labeling the data, the address, and control bus paths correctly. The arrows need to be shown. I would argue this diagram doesn't make a great deal of sense, but there you go. Identify all the components correctly. Even those upside down trousers need to be correctly labeled despite the fact the symbols don't seem to mean anything. Using the accepted drawing conventions for the CPU, so using the symbols they've suggested. Upside down trousers for ALU, rectangle for registers, and an oval for the control unit. Everything else seems like it can be a box. Okay, describe the function of two of the buses involved in the fetch execute cycle, so 4 marks. How would we do that then? Well, we're going to have a mark for naming and a mark for describing the function of any 2 buses. That seems quite straightforward to me. The address bus is used to transmit the address in RAM of the next line of program code to be fetched. Used to transmit the address of a RAM location or the input-output port where the data is to be stored or loaded. So it essentially transmits the address, but with a bit more detail. The data bus is used to transfer the data, but it's the program code between RAM and the processor, or data between the processor and RAM. The control bus is only used for control signals from the processor to the RAM, or the input-output ports to start data transfers. It also carries the interrupt signals when something requires specific attention. Okay, explain the sequence of operations that will occur during the execute phase of the fetch, decode, execute cycle, making clear the role of the program counter, the memory address register, and the memory data register. All right, so what do these things do then? Well, first of all, the program command is taken from the current instruction register. The processor then carries out the action which depends on the command. When it's completed, the program counter is updated, ready to fetch the next command. 1 mark for stating the program instruction is held in the current instruction register. That should be the world's easiest mark. 1 mark for correctly describing a load or save operation, making sure to reference the memory address register and the memory data register. And 1 mark for correctly describing one other processing operation, like calculation, logic, or jump operations. Calculation is arithmetic, logic is ands and ors and nots, and jump is actually moving the program counter. In other words, moving which line of code we're going to go to next. 1 mark as well for stating the program counter is incremented at the end of the execute phase. Question 9. A large and complex computing task needs to be carried out. Programmers consider 2 possible solutions, using parallel processing and distributing processing on smaller computers. So this is the parallel processing question. You might have noticed no slides. That's because it's better explained through a past paper question. Parallel processing, remember, is where we split the job up amongst multiple cores or sometimes multiple CPUs or multiple computers. Okay, so parallel processing is splitting a task into processes that can be run simultaneously on multiple processors. It's that bold and italicized word there, simultaneously, that's important. Identify a process which must be run sequentially. So that's one after the other, and schedule in the parallel and sequential tasks to run in the correct sequence. So we do the sequential stuff, then the parallel stuff that relies upon that. Distributed processing is a little bit different. It's where we load programs and necessary data onto a number of different machines so they can be run independently, and we pull the output together and work out the answer from there. Part B, discuss the factors the programmer might consider when making a choice between parallel and distributed. So whether I split the job up and do it on this machine, or whether I split the job up and do it on multiple machines. There's a bunch of stuff here. But first of all, how much computer equipment have we got and what have we got? We might be a business where we've got a quiet time on weekends, in which case distributed might be better because I've got all these computers sitting unused on the weekend. The suitability of the programming task. Can I split it up? Is it parallelizable? That's an important question as well. The amount of work required for the IT staff to load the programs and data onto multiple computers. Is it coordinated with a single program, or am I expected to be able to manually go and put the parts of the program on different computers myself? Availability of local area or wide area network to transfer that around again. And again, the effect on the other work of the organization. Am I going to be taking up processing time from our mainframe computer? Is it supposed to be doing something else? In which case, probably best not to use it. The final thing is security or resilience considerations. There's a lot going on here, but it's mainly questions about whether we have the equipment or the time or the ability to do a distributed process. You'll see there's only really one question about whether something can be parallelized or not. So guess which the most common one is. You're shockingly right, it is parallel processing. Here's another parallel processing question. They love asking these. Explain the meaning of the term parallel processing. Your answer should make reference to how parallel processing carries out a single task. But let's have a look. You're going to have 1 mark of each of these. So, first of all, parallel processing is two or more processes working together to perform a single task. We split the task into smaller subtasks. The technical term for that is thread. They're executed simultaneously, that keyword again, by the processors. And then for 4 marks, give 4 limiting factors of parallel processing. So what makes parallel processing not quite so good? Well, 1, it's more complex to program. Making asynchronous programs is really quite difficult to think about. Multiple processors might not be available. You might have a computer with a single core or single processor, so you have to keep that in mind. Software might not allow parallel processing. Advantages might be minimal because the processing speed increases might mean that we're not really seeing a difference. Now, sequential processing is still important. So if most of the algorithm is sequential, we're probably going to see very limited speed gains from going to all the effort of parallelizing the algorithm. Not all tasks are suitable for parallelization. Now, multimedia tasks tend to be. It might be less efficient overall due to the introduction of functions not needed in an equivalent sequential program, things to maintain and keep track of where the data is and if it's completed. You wouldn't need that in a sequential program, but we would need it in a parallelized program. Assembly language. Now, assembly language, I'm going to explain to you and go back through the GCSE style of this for a moment. Assembly language is any combination of instructions like this, along with memory addresses. We've got input and output, which take an input or output. So input takes an input value and puts it in the accumulator. Output puts the accumulator on the screen. Dat means data. STA stores a value in from the accumulator. LDA loads a value into the accumulator. Operations add and subtract will surprise you with what they do. I'm only joking. It's add and subtract. Halt stops the program. BRA or JMP is branch or jump. BRZ or JMZ, jump on Z, branch on 0. So in other words, if the number in the accumulator is 0, I would jump to a different place. BRP, positive, branch on positive, which means jump to a different place if the answer in the accumulator is a positive number. Those bottom two are how we get if statements built in. Let me give you an example of a times table calculator. Key things. The instructions on the left, our program counter on the top and our accumulator on the right. And we'll see where we are in the fetch, decode, execute cycle. This is a very simple program. We're going to input first of all. And notice when we fetch, we're looking at where the program counter is. And once we fetched, we increase the program counter. Decode means what is that? Well, that's input. We're going to take whatever the user said and put it into the accumulator. Execute is actually do it. So let's go and do it. So the user's typed in 9. That's going into the accumulator. Boom, happy days, I'm done. We get back to fetch. We go to the program counter and say, where are we going next? So we're going to line 2. That done, the program counter increments to point to the next instruction. I then need to decode my instructions. STA7 means store the value from the accumulator in line 7. So I'm going to put that 9 on line 7. Watch it go. Notice it just replaced the number part, not the instruction part. Next, with that done, we go to our fetch instruction again. Our next line is 3. Then we increment the program counter. This instruction decoded means load from line 8 into the accumulator. Line 8 is the value 0. Let's pop that in the accumulator. Done. Fetch means looking at line 4 next. Add 7. Now this is where people get confused. Add 7 doesn't mean add the number 7. It means add memory location 7. So essentially what that's saying is it's going to be the accumulator plus 9, because that's what's in memory location 7. 9 plus 0 is 9, and that gets put in the accumulator. Our next thing is our output command. That just outputs whatever's in the accumulator on the screen. And then we go to our branch instruction. Now you might have jump, this is branch. What it means is sets this instruction, all that does is it sets the program counter to the value in it. So we're going to change our program counter to the number 4. And what that's basically saying is go to line 4 next. Now this is the clever part. When we fetch next time, because we always fetch from the program counter, it's telling us to go to line 4. We increment the program counter. So branch instructions are really good for sending us back. This time we're adding from memory location 7 again. So this time it's 9 plus 9, which is 18. Pop that in the accumulator. Output from the accumulator on the screen. So 18 appears on the screen. Branch again, so that's set the program counter to the number 4. Then next time we fetch, we're going to go to line 4, add from memory location 7, another 9, that's 27. Output that number, which is 27, and then branch back to line 4 again, changing the program counter to 4. When we fetch it, we go back. Now, this is an infinitely looping program, so we could do that forever. So before we do that, let's have a look at labels, because labels are also quite important as well. Labels are a way of making a program easier to read. This is the same program with labels. You notice on the left-hand side, we've labeled our lines. So instead of having to do store on line 7, I'm saying store in the table. Instead of saying load from the start, I can, load from line 8, I can say load from the start. And I can say branch to the loop. All the computer does behind the scenes is it goes and checks where they are and turns those into numbers. So the computer runs exactly the same program it always was. But for a human, labels make a bit more sense. This is what you get in your exam question, though. They don't give you a standard assembly language. They give you one that they might have made up or a random one. They give you a bunch of instructions, and your job is to write a program that does something using those. So in this example, write a program to input a number of daily rainfall readings for a weather station ending with a rogue value of -1. So you're going to chuck a bunch of numbers in, you're going to type in -1, and that will tell it to stop. The program should then output the total rainfall and the number of readings. Okay, so we need to make sure that as we're inputting the values, we're adding those values together and counting how many there have been. This is an example of what you might get. You might initialize your readings to 0, initialize the total. I notice they've used labels here to make this a bit easier. They might input the value. If it's negative, jump to the finish, and you'll see the finish at the bottom here as output of the total and the count. But if we're not finishing, we're going to increase the reading count, add the reading to the total, and return to the start. There's a mark for initializing, 2 marks for the loop working correctly, and a mark for the correct calculation of total. There's also a mark for correctly calculating the count, and there's a mark for the input of readings and output of total. So even if you can't get this, you could do the initialization, the inputs, and the outputs, and you'd get 3 marks. Here's another one. They're broadly similar styles. In this case, it's a lab experiment. A series of positive numbers are entered, and a negative rogue value is used to terminate. So again, any amount of numbers can be typed in. The moment we see -1, we're leaving. And again, we're outputting the total and the amount of values. It's looking very similar, isn't it? It's almost like it's been copied and pasted. Again, a mark for initializing, a mark for labels to make the start of the loop, 2 marks for the loop working correctly, a mark for updating the total of the count, and a mark for outputting the total of the count. Very similar to the last one. Here's another one. Oh, what a surprise. Very, very similar. Let's do part A. Write a simple program using the commands above to output the integers 0 to 9. So that is a little bit different. Now, it's already told us that memory location 1A has 0, 1B is 1, and 1C is 9. So we're going to have a mark for outputting a digit, a mark for incrementing or decrementing the output values, so either you're going up or you're going down, 1 mark for jumping back, 1 mark for a working solution. So you'll see in this case, what we're doing is clearing the screen. We're loading 1A, which is 0, into memory, outputting it, adding 1B, which is 1, storing it back in 1A, and then loading 1C, which is 9. We're doing dec then, which is decrementing the accumulator contents. That goes from 9 to 8 and storing it back in there. Now, JGT jump, that jumps the label if the contents of the accumulator are greater than 0. So as long as we are still counting down from 9, we're going to jump back up and keep doing that until we get to the bottom and then end it. 2 extra commands added. Demonstrate what those bits of code are doing. Well, I mean, it's reasonably straightforward. Register R, S, R, accumulator. These are just the values that are changing based on those instructions. So it's worth applying those to those answers. Next topic, the operating system. Okay, we need to explain the following types of system. Let's go through them. Batch processing systems basically store similar repetitive tasks to process in a batch. So basically all at once later. Normal batch processing systems click over into processing mode at a certain time of day and will be storing the records for the actually active working hours. Some systems just store records for months and months and months and then process them all in one go, because good examples of this are calculating your energy bills. They're calculated roughly every 3 months. Every day, your energy reading is sent to the system and it is stored and is only calculated at the end. Bank transactions are the same. Your bank transactions happen throughout the day, but the money is only moved at the end of the day. A single user operating system is one where you're only allowed one user at a time. You can't use the system unless the first user logs out. And this isn't like your computer in the classroom in school. This is more like your computer at home, where no one else can use that device at all unless you log out and they log in with their user account. Multitasking is where the operating system looks like it's running more than one program or process at once. Now, in reality, what it's probably doing is it's flipping between different applications so quickly that you can't see the difference. Because computers, remember, can do billions of things per second, but you are not going to be able to see that. It's only where you have multiple cores that true multitasking actually happens. Let's use a past paper question to explore multi-programming and multi-user. Okay, so 1 mark for the definition. So a multi-user operating system is one where a single computer has a number of separate users running separate processes from different terminals. That's a bit more like what you have in school. A 1 mark for mentioning the concept of time slicing. So because multiple people are trying to use one CPU on a server, the server's having to time slice. It's having to give a little bit of server time to everybody on the system. Now, active processes may be running, so they're having processor time. And if the processor is available, they get it, or if it's suspended, they don't. A suspended process might be waiting for something to complete, or linking to something, or, waiting for a printer to finish. We'll extend that a little bit by talking about how it actually works. Schedulers can help with this, because remember, it's trying to flip between different processes as quick as it can. You could have a single query with equal job priority, or you could have a multi-job queue, so different jobs have different priorities. Small jobs get done quicker, large jobs get seen to slower. You might have polling, so check to see if the jobs are ready to go, or if they come back in the queue and kick them out if they're not. You might have storage protection to make sure that programs in RAM don't interfere with each other. You might have the back install disks provide virtual memory to extend the job queue. There's also a separate spooling system that handles I/O when you're dealing with the terminals, because they'll be at a different speed to the main processor. And a large mainframe will have multiple processors, so it might run multiple threads at the same time. Now we need to talk about interrupts, talk about the conditions, what they are, and how they work. And again, the best way to do this is by looking at the past paper questions, because they do love to repeat themselves. An interrupt in a computer system, well, what is it? Well, an interrupt is this. It's a signal sent to the CPU that attention's required somewhere else. It might be hardware or it might be software. 2 instances where an interrupt would be generated and the resulting action would be taken by the computer. Okay, so in this case, a keyboard, a key press would cause the CPU to accept characters which may be transferred to whatever program is currently at the foreground. A mouse click might cause the program to activate a menu choice. A printer might have done its processing and ask for the next block of data. A disk drive might have completed transferring the data, making the CPU to start the next copy. A running process might have done, so the CPU can start reallocating its resources. A process might have timed out, so it can be killed by the CPU. A program might have requested data, so the CPU might need to get the disk to actually copy things across. A file error has occurred, so the CPU can suspend data transfer and show a warning on the screen. Or the user has requested a process to close, so the CPU updates the screen display and reallocates resources. How do you deal with interrupts then? Well, because an interrupt is basically an instruction that says something's happened, the interrupt joins the queue of instructions that we're currently working on with the priority. If the priority is higher than the instructions, we get to it quicker, because remember, these instructions are being fetched, decoded, and executed, just like we've just seen in the assembly language part. If it's important, it'll jump to the top of the list if we're caring about priority. If that requires multiple steps to deal with, the current list of instructions might just be dumped into an instruction stack somewhere else on the CPU and then reloaded and resumed later. Here's a bit of a random question about a double buffer. What's a single buffer and a double buffer, and why do we care about them? Well, a buffer is a small block of memory inside a hardware device, okay, and it holds the data sent from a device. Double buffering is used when we're emptying one and filling another. So the idea being that the hardware device never has to stop because one of its buffers is already full. It'll be therefore active much more often than if we were having one buffer which would fill, empty, and need to be filled again. Last topic. The need for different types of software and their attributes. Okay, so first of all, a bunch of different types. Two of these will look at past paper questions. A safety critical system. We're going to start with control systems. So what are control systems? A control system is any input or output and that deals with automated trains. So for instance, monitoring speed. A control system manages what's happening. So it would apply braking or acceleration as necessary. It might check where they are, applying brakes when we get into a station. It might check the track ahead and brake if there's something in front of us. It might check the doors and not allowing the driver to move from the platform if the doors are open. It might monitor the fire warning systems and slow down and stop and open all the doors if a fire is detected on board. That's what a control system is. It controls and automates part of a physical device. We'll look at that in a bit more detail in a second, but safety critical systems, that's where the majority of the marks come from here. What is meant by safety critical systems, and describe measures that are involved in ensuring safety? Okay, well, a safety critical system is one where a malfunction or a failure of computer hardware could potentially put people at risk of injury. One of the measures that is involved in ensuring safety is exhaustive testing must be carried out. So they really are tested to the nth degree, a safety critical system. Systems also need to have redundancy. There's a backup copy of software or hardware that kicks in if something doesn't work. They should be designed to be fail-safe, like a train will come to a halt if a malfunction is detected. Self-driving cars, if they freak out about something, pull themselves over to the side of the road and hand control to the driver. Regular maintenance and testing should be carried out to make sure that nothing's breaking. And then importantly, we need a high level of security to guard against malicious attacks. You wouldn't want your Tesla to be hacked into and some script kiddie sends you on a self-driving journey across the country which you can't unlock your doors or get out of or interact in any way. Control systems then, it's any system that controls the behavior of another one. A good example is maintaining the temperature of a greenhouse. It needs to use temperature sensors and then decide when to cool and when to heat. And I suppose the same could be said of a shed as well. Key input and output devices here are sensors for the input and actuators for the output. They are motors, they are things that move something in the real world. Another past paper question on expert systems. Okay, so what are expert systems? The point of expert systems is they store a bunch of knowledge as an expert would. You answer questions on something and they suggest problems or suggest fixes to you. What are the benefits? Well, it's definitely going to be able to store more knowledge than one single person. It can be kept up to date easily and help to give us more accurate decisions. It doesn't get ill, retire, go on holiday. It's always there for us. It's also really good to help us get a second opinion on something. It's always available. This is quite important. It allows access to an expert where it's not available locally. So if you haven't got a specific kind of doctor on site, an expert system loaded up with that knowledge can at least give you some indication of if you're in the right ballpark with what you're trying to diagnose. Provide significant clerical time and labor savings, certainly, because you're not having to deal with manually organizing any of that. Good competitive advantage, or makes things more efficient because we have a system doing things for us. We can centralize decision making, so we can look at what the expert system says and decide from one location what's happening with something. We can even allow people at a lower management level to make decisions because their management time is better used because the expert system can suggest for them to do things. It also allows us to more broadly distribute expertise through the company, and a good expert system explains its decisions so the user can decide whether to accept the answer or not. Expert systems, if programmed correctly, can also learn from their experience. It also allows employees to learn from the system. Now this topic here, wide and local information exchanges, honestly, it's the most generic type of program you've ever seen. Try Googling that. You get some random stuff. There's no guidance provided from the WJEC. It's not even in the textbook. I can only assume that these are things that allow us to share information in different geographic regions. So for instance, all the schools in a certain LEA would need to share information with the LEA about attendance and grades and things like that. And that's what a local information exchange system might be for. The wide version of that might allow information to be exchanged nationally or internationally. Now, the thing with that, you'd have to ensure consistency and standardize on the information that's stored and the format and stuff like that, so that data could be transferred more portably and wouldn't need to be converted between each format. Almost there now. Internet and intranet. Now, first of all, what's the difference? The internet is the wide internet where you can browse from anywhere, and an intranet is a version of the internet that is only visible from one location. So your school may have this, where you have a series of web pages that only you can see when you're in your school. We're going to have a look at what a search engine does, look at some common contemporary applications. Once again, the term contemporary is a bit flexible in this. And then talk about the possible effects of the internet upon professional groups in the wider community. Now, I think this unit, a lot of it is common sense. I say common sense. If you're interested in computer science, I think you will understand and be able to talk about a lot of this in some detail. Already, you probably don't need any help on it. But there's also never been a question asked about this formally on any exam, so it's going to be hard to tell you how to construct an answer for it. And it's a lot. Let's have a quick look. Search engines search for content on web pages and then display a list of web pages that match. I mean, I don't know what more you want me to say. You know what a search engine is. Google almost became a verb at one point. In fact, it probably is, as much as Google are trying desperately not to. What search engines do is they index the web. They basically build up a map of how all pages link to each other. Then they apply a page rank algorithm. And what that does, identifies the ranking of a page based on the importance of the page itself and the importance of how many important pages link to it. And you might think that's quite difficult to do, but that's why it needs to be recursive. Once we've worked out how important a page is, we go and work out how important all the pages are that it links to, and so on and so on and so on. And that helps us reconsider how important we thought that page was in the first place. Contemporary software, this is what it recommends looking at in the textbook. Aside from that, I don't really know what to talk to you about. Presentation software, something like PowerPoint. Don't use the brand name when you're talking about it, but you get the idea. You put a bunch of slides and you present them to someone. Desktop publishing software like InDesign or Publisher lets you make things that are designed for paper, customizing it with wrapping text amongst images and all that sort of stuff. Spreadsheet software like Excel helps you make calculations and work out cost savings and comparisons, stuff like that. There are two types of drawing software you need to know about. Vector-based tools like Adobe Illustrator, where the mathematics are stored so you can zoom in or zoom out infinitely on any image. The problem with that is they're not quite realistic. A realistic image is made by a bitmap. A bitmap editing piece of software, something like Photoshop, allows you to edit photographs. The problem with that is you zoom in too much, things end up pixelated. Database software like, I feel dirty saying it, but MS Access or like MySQL, as we've used, allows you to store data in a format that is useful. Animation and 3D rendering, then like Adobe Animator, which used to be Flash, Maya, 3D Studio Max, bunches of stuff there for creating 3D characters or even 2D characters and animating and rendering them. And then there's even a category in the textbook for mobile apps. And if you don't know about mobile apps, I don't know what to say to you, honestly. Finally, what effect does the internet have on professionals in the community? Well, there's a lot, isn't there? There's a lot of an effect that it has. So have a think about it. But the question will probably have some context, just some ideas for you. Okay, like information. You don't need to memorize things anymore. You can just Google for stuff you want. But that means the skill set that a professional needs to be more complex. Like you need to be able to do data analysis and applying a skill you read about, because just being able to recall information is not an important skill anymore. It also allows us to pick a format for how we communicate with other professionals or other people in our organization. Synchronous or asynchronous communications, in other words, synchronous, I'm speaking and they're speaking back, things like video chat, audio chat. Asynchronous communication, email, things like Discord and Slack then for the text-based communication would be useful in that regard. Web or social media presences are now required for all businesses, no matter how big or small. And then it becomes difficult to manage your social brand because the way in which your business is perceived can be affected by good reviews or bad reviews. You may want to improve your page rank to make sure you get to the top of Google, and that's a job in itself. And there's another question about professionals and community. It's like, how do you prove plagiarism, which is so easy and ubiquitous? And I suppose the sub question to that is, does it even matter? Now, that is it. That's all we have to talk about for those partial units in Unit 4 WJEC Computer Science A-Level. I don't know what questions they're going to ask. Some of the bits they've left in would be difficult to ask a question, and we've never seen a past paper question for it. But I'm expecting to see an assembly language question very much in that same vein, so go and practice that. And there are going to be bits and pieces from all the bits we've looked at today, so go and review that video, review those past paper questions in particular, and make sure you're as aware of this information as you were the full units that we've covered. Don't forget, there's a revision session live at 8 PM just before the exam on my YouTube channel and my Twitch, where we'll go through in as much detail as we can the Unit 4 content as a bit of a last-minute revision. Good luck to you guys. You won't need it because you're amazing. Keep revising.